So we're going to use Newton's method for doing the optimization involved in logistic regression. And Newton's method is such a useful technique that's applicable in so many optimization problems that I thought it is useful to do a discussion of it on its own. So let's start with what Newton's or Newton-Raphson method is. So Newton's method. So the context is, let's start with one-dimensional. So we are optimizing some function, f of x, and Newton's method applies when we are sort of close to the optimum we are seeking, and then it converges sort of breathtakingly fast. So the best way to think about it is that we are doing a quadratic approximation for f of x around its optimum. So suppose it's like this, and it might be doing other things out there, but we are pretty close to this bowl. I'm thinking of this as a minimization problem, but Newton's method also can be applied for maximization. Okay. So at this minimum of f of x, its derivative should vanish. So let me define its derivative as g of x, which is f prime of x. So what we are really seeking here is actually the root of g of x. So this guy here, x opt, at x opt we have g x opt equals 0. So we are really doing root finding, and the quadratic approximation for f of x around its optimum is equivalent to a linear approximation for g of x around x opt, right? So let me draw a line here, right? So basically f of x has a negative slope before x opt and a positive slope after it. So if I look at g of x, it will look like negative before, positive after, and because it's minimum, of course, and it will look like this locally, right? So this is what this is x, this is what g of x looks like locally, right? So the idea of Newton's method is, if you start from a point, you're not quite at the root yet. If you start from a point x0, how quickly can you get to the root x opt here? X opt, because of course we are talking about the original optimization problem, but root finding is a thing in and of itself also. So okay, so well, let's look at how far up x0 is. It's gx0 up from there, and how far we need to travel along the x-axis to get to the root. So in this picture where it's actually truly a line, I can get to the root in one step because I know that the slope of this line is g prime of x0. So I can just directly get to the stop by saying, okay, I need to travel basically gx0 over g prime x0 in order to get directly to the root, and I need to travel leftwards. So if I do x0 minus that, I get x1, and in this particular case x1 would be equal to x opt, but in general we iterate, right? So that's my iteration. So let me write it down systematically. I have f of x to be optimized, g of x is f prime of x, and the Newton iteration is xn plus 1 equals xn minus g of xn over g prime xn, and of course that is the same as xn minus f prime of xn over f double prime of xn. So we are proceeding really fast, assuming that the derivative is like a line, and I'm going to box this because this is the form that we need for the optimization problem. So how does it generalize to more than one dimensional? So data. So Newton method in d dimensions, right? So we want to still optimize f of x, where this x is now x1 through xt. I can think of it as either row or column. Let me say column for now. And what I want to find, I'm gonna g of x is the gradient. I want to the gradient of f at x. Of course, it's defined as let's see, del f by del x1 down to del f by del xt. And what I would like to find is find x opt such that g of x opt is 0. So now we are trying to find the root, and then this is a vector 0. Now we are trying to find the root of d different functions that are basically the components of the gradients in the different directions, right? So we are going to do the same thing that we did in one dimension, which is basically say, okay, now each of these GIs I'm going to approximate as linear. So if I am looking at a point x0 and expanding around it, then gix minus gix0 will depend linearly on x minus x0. Well, so it depends linearly, but it can depend differently for different components. So basically, for the component XL, GI would vary as locally as del GI by del XL, and then you would multiply it by the difference XL minus X0L. So you basically have this summation of d terms that I'm showing here, the summation of d terms that corresponds to the linear variation of gi of x, the local linear variation around it. And of course, what are these partial derivatives that I've written? I mean, this is del gi by del xl is simply the Hessian matrix for the original f, which is basically the del 2 of fx. And then in order to get the ith component of the of the gradient, I had del xi, and then I differentiated with respect to the lth component, and that's the del xl, right? So that's the Hessian matrix, which is a d by d matrix as we go along. So what do we have here now? So we now have the equation, the writing everything in vector form. We have this vector gx minus the vector gx naught, which let me also write it as the gradient of f at x minus the gradient of f at x naught is the Hessian at x naught times x minus x naught, right? And in order for, and if you basically say, okay, I'm trying to find the root, I'm trying to go directly to the root where this gradient, let me change my pen to red, where this term becomes 0, well, the solution for that has to be exactly analogous to what we had before. x1 is going to be x0 minus the Hessian at x naught inverse times del f at x naught. You can check that that's the case. Let me go back to the blue pen and write down the final result for the general Newton iteration is xn plus 1 is xn minus the Hessian xn inverse del f evaluated at xn, and that is the Newton iteration. And it is quite amazing how fast it converges if the conditions are actually right, and it can completely diverge if the conditions are wrong. So basically, as long as you're close enough to the optimum that the quadratic approximation on the function is not bad, you can converge amazingly fast, sometimes in 4 or 5 iterations, whereas gradient descent might take you ages, right, depending on the step size you choose. One last thing you need to be careful about is nothing in this derivation says that we are going to the minimum of the function or the maximum of the function, right? All we are saying is that the quadratic approximation, but it could be either convex up or convex down near the local optimum we are seeking. So the only way you can check whether it's a maximum or a minimum is to look at, in the 1D case, the sign of the second derivative, and in the 2D case, whether the Hessian is positive definite or negative definite. And I'll let you think about which way is which. So now that you've thought about it, I'm going to give you the answer anyway. Basically, if I have a minimum like this of a function f of x, and this is x opt, we know that if it's a minimum, the slope before the minimum is negative, and the slope after the minimum is positive. So basically, you have that the second derivative is bigger than 0. For a maximum, by the same reasoning, the slope before is positive and the slope after is negative, and so the second derivative is less than 0, and the natural generalization is that the Hessian for a minimum is positive definite for minimum, and the Hessian is negative definite for a maximum. Right, so that's the check, but just wanted to emphasize that the Newton method is equally valid for seeking maxima and minima, as long as you keep this in mind.